In our first 4 lectures, we discussed the counting numbers, fractions, decimals, percents, the integers, and the irrationals. And now we'll conclude our arithmetic section of this series by looking at the imaginary and complex numbers. The imaginary numbers are much newer than the irrationals because it took a while for human beings to be able to create enough situations where they needed to use imaginary numbers. Now, what is an imaginary number? Well, suffice it to say that a real number is one that when you square it, you get 0 if you started with 0, or you get a positive number. It is impossible to multiply a real number by itself and get a negative. So what would happen if you needed to take the square root of a negative? And in 50 AD, we see the first writing that hinted at the understanding that these things existed, these square roots of negatives. And that was with Heron of Alexandria. Remember, Alexandria in Egypt was the real seat of knowledge. And Heron presented a problem that we would write as 81 minus 144. And he was looking for the square root. And since 81 minus 144 is negative 63, Heron was writing about the square root of a negative number. He didn't know what the answer was, but it was present. Numbers that were square roots of negatives were eventually called subtle numbers because they obviously you could not even see them. So they were subtle. And finally, in 1637, one of the giants of modern mathematics, René Descartes, first used the term real and imaginary, since a number that was not real was imaginary, because the opposite of real is imaginary. And he used that to differentiate between numbers that, if squared, produced a positive or a 0 number, and numbers that were squared produced a negative. Euler, Leonhard Euler, very famous mathematician who we've mentioned already and we will continue to mention. Euler was the first one to use a symbol to represent this square of a negative. And he said that the square root of negative 1 was I. And that was in 1777. So it was 140 years from the time when Descartes said these numbers are imaginary until someone came along and used a symbol that was accepted. And remember, Euler was so respected that when he used a symbol, it was immediately adopted by all people who were working in mathematics or the sciences. Once imaginary numbers came into common use, it was a natural consequence for the combination of a real number and an imaginary number to be considered. And these are your complex numbers. Girolamo Cardano, an Italian mathematician, posed a problem in 1545. And what Cardano asked for was 2 numbers whose sum is 10 and whose product is 40. I mean, you add them, you get 10, you multiply, you get 40. No 2 real numbers work. And what Cardano said was that the answer was 5 plus the square root of negative 15 times 5 minus the square root of negative 15. And that would give you, when you multiplied it out, 40. Because the 5 times 5 is 25. And again, you'll notice these are conjugates because they have only difference is the difference in the sign. And the square root of negative 15 times itself gives you negative 15, but a plus times a negative gives you a negative 15, which is a positive. So we have 25 plus 15, which is 40. And obviously, adding the 2 numbers, we get 5 plus 5 is 10, and the 2 square of negative 15s cancel since they have opposite signs. So the answer to Cardano's question were 2 complex numbers. But remember, it wasn't until the 1700s that Euler put a symbol for this. And people wrote as the square root of negative 15, for example. And no one thought different, and no one knew what those numbers looked like. They just continued to use them. And this is true many times in mathematics, where people create new number systems just simply to answer a question or a what if kind of thing. And then later on, someone gives it a symbol, and then later on even, someone finds a use for it. Well, finally, in 1831, Carl Gauss, another brilliant mathematician. In fact, I've been told that Carl Gauss, who was a German, was the last human being to know all the mathematics that existed in his or her time. Because today it would be impossible. Today, this very day, more mathematics is being created than one person can learn in a lifetime. So Gauss was a pretty amazing fellow. Of course, there wasn't a whole lot of mathematics back in the 1800s compared to what there is today. But he first used the term complex and wrote numbers in the form of A plus BI, where A was a real number and so was B, and therefore BI was imaginary. A plus BI being a complex number. A purely real number would be written as A plus 0i. The imaginary component would be 0i, therefore making it a real number. A purely imaginary number would be written as 0 plus BI. That is, the 0 goes away and you're left with BI, a purely imaginary number. It was discovered that by multiplying A plus BI times A minus BI, what you received was a product of A squared plus B squared. The imaginary part had gone away. A squared plus B squared is a real number. In 1821, Augustine Louis Cauchy, Augustine Louis Cauchy was the first to use the term conjugate. And this is a term we've used in previous lecture, talking about irrationals. But he was the first one to use this, and with A plus BI multiplied by A minus BI, and eventually became to be generalized to any form of numbers. We have two terms, and the only difference was the sign in between the two terms. The development of complex numbers, that is, numbers of the form of A plus BI, required algorithms for the addition, subtraction, multiplication, division of such numbers. And we're going to look at those right now. The rules of addition are true for no matter what kind of numbers you're using. You must align place values and add along those place values. So in this particular case, we're going to add the real part of the complex number to the real part of any other complex number, and the imaginary parts will be added also. The sum of the real parts will give us a real answer. The sum of the imaginaries, unless they cancel out, will give us an imaginary answer. Here are two examples. 8 plus 3i plus 6 minus 7i. 8 plus 6 is 14. 3i plus a negative 7i is negative 4i. So our answer is 14 minus 4i. Pretty simple, nothing very difficult. The rule of addition holds. Second problem, 9 plus 8i plus negative 11 plus 3i. Well, and then when we add to that, we'll add to that a 4 minus 7i. So now we have three numbers to add. Doesn't make a difference. We add the reals, 9 plus a negative 11 plus 4 is 2. And we add the imaginaries. 8i plus 3i minus 7i is positive 4i. So the answer is 2 plus 4i. The rules for subtraction, again, are the same as addition. We subtract reals from reals and imaginaries from imaginaries. Two more examples. 9 plus 6i minus 7 plus 2i. 9 minus 7 is 2. 6i minus 2i is 4i. So the answer is 2 plus 4i. Using negative numbers doesn't make a difference. Again, we still subtract with the same rules we use for integers. If we have negative 7 plus 12i, minus 6 minus 3i, negative 7 minus 6 is negative 13. 12i minus a negative 3i is positive 15i. So our answer is negative 13 plus 15i. In multiplying numbers, any kind of numbers, we always multiply each part of one number by each part of the other number. Multiplying digit times digit and place value times place value. Of course, with numbers expressed as complex numbers, the digits can be multi-digit numbers. Those of you who are familiar from your algebra class in high school with the FOIL method, you can use that very, very nicely here. An example, 2 plus 3i multiplied by 4 minus 7i. And here we get 8 by multiplying the 2 times 4. 2 times negative 7i is negative 14i. 3i times 4 is positive 12i. And the positive 3i times the negative 7i gives us a negative 21i squared. Now remember, I squared is the square root of negative 1 squared, which would be negative 1. So a negative 21 is a positive 21. So we wind up with 8 minus 14i plus 12i plus 21. And combining the terms, we get a real answer of 29 and an imaginary part of negative 2i. So what we have is 29 minus 2i. We multiplied a complex number by a complex number, and we wound up with a complex number. It should be noted, again, in talking about the multiplication, when we multiplied a positive imaginary, that was positive 3i, times a negative imaginary, negative 7i, we eventually wound up with a positive real product. So a negative imaginary times a positive imaginary is positive. Quite different than dealing with the real numbers, but again, that's because the I times I gives us an additional negative sign in front of our answer. Squaring a complex number is accomplished in the same manner. For example, 2 plus I quantity squared. That is 2 plus I times 2 plus I. 2 times 2 is 4. 2 times I is 2I, and then I times 2 is 2I, and I times I is negative 1. We combine the 4 and the negative 1 and get 3. Combine the 2i plus 2i, we get 4i. So the answer is 3 plus 4i. And again, as we said, multiplying a complex number by its conjugate will give us definitely a real answer. For example, 3 plus 6i times 3 minus 6i gives us 9 plus 36, which is 45. So multiplying two complex numbers gives us a real answer, in this case, a positive integer. Division of complex numbers is accomplished in a very similar manner to how we divided irrationals. We simply take the denominator, find its conjugate by changing the sign in the middle, and multiply the top and the bottom of the fraction by its conjugate. And therefore, we will multiply, we should be dividing for us. Let's look at the division problem. The division problem is 2 plus 3i divided by 1 plus I. Well, 1 plus I is in the denominator. We are going to multiply the top and the bottom of that fraction by the conjugate of 1 plus I, which is 1 minus I. And in multiplying 2 plus 3i, the numerator, by 1 minus I, we wind up with 2 plus 3i minus 2i plus 3, which simplifies to 5 plus I. The 1 plus I times the 1 minus I gives us 1 plus 1, the real number 2. So our final answer to the division problem, we started with the division problem. What is 2 plus 3i divided by 1 plus I? And the answer is 5 plus I over 2. If that doesn't look like a complex number to you, you could also write that as 5 halves, or 2.5, plus 1 half I. Again, a real part and an imaginary part. So dividing simply uses the conjugate, and we really don't have a division process. The use of complex numbers led to new answers to old problems. And that's what happens in mathematics. When we create a new type of system, we go back and look at previous questions and say, have we totally answered the question? And in many cases, the answer is no. We now can create new answers. And in some cases, the question to follow that answer would be, what does this answer mean? How are we going to use it? But again, remember, much of mathematics is created purely for the mathematics. And then years later, possibly hundreds of years later, someone finds a practical use. So anytime you see mathematics and you say, when will I ever use it? The answer is, you may already use it. You may use it in a certain situation, or no one knows, but someday, if you hang around long enough, you will use it, or someone will. Well, if there are 2 square roots to a number, why are there not 3 cube roots to a number? Now we know, for example, most positive numbers, for example, 4 has 2 square roots, 2 and negative 2. 0, of course, only has 1 square root. But how about the cube root of 1? Well, you say the cube root of 1 is 1. That's it. There's no other number, real number, multiplied by itself that gives us 1. But wait a second. Why can't there be 3 cubes? If there's 2 square roots, there should be 3 cube roots. And in 1629, Albert Girard declared that there should be 3 answers. He didn't have the answer. He just said, hey, there should be. And I think that's pretty neat, because here was somebody who said, look, everything we've done in the past may not be right. We need to look for two more answers. Well, it took a few years, from 1629 to 1730, 101 years later. Abraham de Moivre, a French mathematician, produced a method to find the other two cube roots of 1 that are not equal to 1. And his method led to conjugate answers. And again, the de Moivre process is learned usually in a trigonometry class. Again, the purpose of this lecture series is not to teach you all the mathematics we talk about. It's simply to either introduce you to something that you've not seen, talk about the development of mathematics you do know, or interest you possibly in then going and taking a course or reading a book to learn more mathematics. And his method provided two additional answers. 0.5 plus 0.5 I, the square root of 3, and 0.5 minus 0.5 I times the square root of 3. And if you cube 0.5 plus 0.5 I, the square root of 3, you get 1. Now, I'm not going to go through the process, but if you actually take 0.5 plus 0.5 I times the square root of 3 and square it, and take the answer you get and multiply it by 0.5 plus 0.5 I, the square root of 3, you will get 1. It seems kind of hard to believe that you could take this complex number, which looks pretty complex. It has an I, a square root, a fraction, and you multiply it by itself and then by itself again, and you wind up with the simple number 1. But indeed, and the same thing happens with 0.5 minus 0.5 I, the square root of 3. When you cube that, you get 1. In fact, it turns out once you show that one complex number works, its conjugate must work, which is kind of neat. And conjugate comes in pairs, obviously, so therefore, for any cube root, if we know the cube root, for example, of 27 is 3, then there are two more complex numbers. One is the conjugate of the other that will also work. That is, when you cube it, you'll get 27. Now, that might not be fascinating to you, but think about it. In 1629, a gentleman makes a statement and says there's got to be two more answers. And 101 years later, another mathematician finds the answers. To me, that's fascinating. And the fascinating thing is probably in that intervening period of time, over 100 years, someone was working on this. And until de Moivre found out, those other someones didn't discover the answer. So a lot of hard work. A graphical representation was allowed for complex numbers once the graph paper, in effect, was created. And that was René Descartes who did that. We'll talk more about graph paper in later lectures. But basically, if we look at the graph of 3 plus 4i and 3 minus 4i, again, conjugates, you will notice a couple things. How do we graph this? Well, first of all, we look at it as the real part, the a, in this case the 3, is the x-coordinate, and the b, the real number in front of the I, is the y-coordinate. So 3 plus 4i is graphed by plotting the point 3 comma 4. And 3 minus 4i is a point that's 3 negative 4. And the interesting thing is we can immediately see that when we have two conjugates, the graph will be, one will be the mirror image across the x-axis, so that one is a reflection of the other across the x-axis. Even if, for example, the real part is negative. If we have negative 2 plus 3i and negative 2 minus 3i, negative 2, 3, and negative 2, negative 3 will be reflections of each other. Let's take a look, if we had graph paper, and we can graph the representations of the three cube roots of 1. We have 1, we have a negative 0.5 plus 0.5 I, the square root of 3, and negative 0.5 minus 0.5 I, the square root of 3. It turns out that these 3 points on the complex plane, where the x is the real part and the y is the coefficient of the imaginary part, fall on a circle of radius 1, and the 3 points are separated by an equal amount, in this case 120 degrees. So That's interesting. And this is part of what Demois was working on. So we could find these roots, and when we look on the graph, we can check that we're correct because they all have the same distance from the origin, in this case, the center of that circle, and they're separated equally. In this case, since there are 3 of them, we divide the 360 degrees in a circle by 3, and we get 120, giving us, when we look at the graph of those 3 solutions, 1 and the 2 complex numbers, we see they're all on the same circle. We see that indeed they are separated by an equal amount, 120 degrees. We know we're correct. And that's a very neat way, a graphical representation to check one's work. And I'm a very graphical person. I like to see things. And of course, I owe a great deal to Rene Descartes because he allowed for us to be able to look at graphical representations of arithmetic and algebra and calculus, which to me is marvelous. Now, the distance from the origin, from 0, 0, to that point in the complex plane is called the magnitude of a complex number. It is very similar to the absolute value. In fact, the symbol that is used is a symbol like the absolute value. And we have the absolute value, for example, of -3 minus 4i would be the point, the -3, -4, which is the representation in the complex plane for -3 minus 4i, the distance from that point to the origin. And if you graph that point and draw a vertical line segment to the x-axis and draw that line segment from the point to the origin, what you create is a right triangle with legs of -3 and -4. But we know that when we take a right triangle, and if we know 2 of the legs, we can find the hypotenuse, and the hypotenuse is the magnitude. And what we wind up with is the square root of -3 squared plus -4 squared. And -3 squared is 9, and -4 squared is 16. A real number squared is positive, and 9 plus 16 is 25, and the square root of 25 is 5. So we would say the magnitude, kind of like the absolute value, the magnitude of the complex number -3 minus 4i is 5. That is the distance from that point to the origin. Using graphical representations of complex numbers, we can easily find what the 4 fourth roots of 1 are. Now we say, wait a second, how can we do that graphically? Well, we know 2 of the fourth roots of 1. There are 2 real numbers that when multiplied by themselves equals 1. One of them obviously is 1. 1 times 1 times 1 times 1 is 1. So it's a fourth root of 1. The other one, of course, is -1, since -1 times -1 times -1 times -1 is also 1. Where are the other 2? Well, let's see. We said in the graphical representation of the roots, 2 things must be true. All the points must lie on a circle, which means they have an equal magnitude, equal distance from the origin. And the points, in this case 4 points, must be equally separated. Well, if you graph the points 1, 0 and -1, 0, those would be the points that would represent the real numbers 1 and -1. Now, they are separated by 180 degrees. They're both on the x-axis. One's on the positive part, one's on the negative part. And they're, of course, 1 away from the origin. The other 2 points, the other 2 answers to what is the fourth root of -1 would have to be positioned to also be 1 away from the origin and to be equally distributed around that circle. Well, it's obvious if the 2 points we know are 180 degrees apart, the point in between them must be exactly halfway in between, because if it was closer to one than the other, it wouldn't work. And what's half of 180 degrees? Well, 90 degrees. So we have a point that is located 90 degrees from the positive x-axis. Well, that's the positive y-axis. And it's located a distance of 1 away from the origin. That point is obviously 0, 1. Wait a second. We said that the y-axis represents the imaginary part of a complex number. So 0, 1 is the point 0, representing 0 plus 1i, which can be simplified to I. So it would appear that I is one of the fourth roots of 1. Let's take a look at the other possible point. And that will be equally located between -1, 0 and 1, 0. But now in the negative part. Well, let's see. It would have to be 90 degrees separated, and it would have to be 1 away from the origin. The only possibility would be a point on the y-axis at -1, 0. I'm sorry, at 0, -1. It would represent the value -I. So the question now is, according to our graphical representation, we have 4 fourth roots of 1. 1 and -1 we know are right, and the other two, which we think are right, are I and -I. Looking at I to the fourth. If I to the fourth is 1, then that is a fourth root. I to the fourth can best be computed by looking at I to the fourth as I to the second power. I to the second we know is -1, and -1 to the second power is +1. That worked. -I to the fourth would be -I to the second, then again taken to the second. And -I squared is -1, because a negative times a negative is positive, and I times I is -1, so we have -1, and -1 squared, once again, is 1. So indeed we have found that there are indeed 4 possible fourth roots for 1, and 2 of them are complex. And again, until we reach this point in our mathematical education, we were blind. We thought there were just 2, 1 and -1. And you may say, well, who really cares? And maybe you don't. But the fact is, complex numbers, although they were worked on in the Middle Ages and developed in terms of symbology and usefulness mathematically in the 1800s, but they finally kind of practical purpose. And the practical purpose, again, unknown to de Moivre, unknown to Gauss, was when we began to transmit electrical current, alternating three-phase current. And that obviously happened in the latter part of the 19th century. And when engineers were analyzing these circuits, there were various characteristics of the circuits, similar to the resistance you have in a direct current circuit, that representation of these impedances, if you will, to the flow of current require a complex number. He said, wait a second. I have a friend who's an electrical engineer. He never mentioned I. I is current. It is. I is what they use for the electrical current passing through a conductor. The fact is that the electrical engineers did not use I for the square root of -1. They used J. And if you look at any electrical engineering text, you will see the use of complex numbers in talking about the characteristics of alternating current circuits. Only instead of seeing 2 plus 3i, you'll see 2 plus 3j. So again, when you see mathematics and it looks difficult and you say, when will I ever use it? You never know. Someday you might. This is the end of the first 5 lectures on arithmetic. Next, we'll have algebra. Let's kind of review what we've done in arithmetic. We've looked at the counting numbers. We've looked at the integers, including 0. We've looked at fractions, decimals, and percents. We've looked at the irrationals. And in this lecture, we finally looked at the imaginary and the complex numbers. That is, numbers that have a constant value. I is always I. 3 is always 3. 3 plus I doesn't change in its value. Beginning in the next lecture, we'll start talking about algebra, where symbols can take on various values. We'll see you in Lecture 6.